Okay, hello everyone. I'm in Maryland right now, near DC, but I know we still have this code here that we're trying to finish up, so I want to go through some hints and stuff like that. I don't think everyone's finished it yet, so there might be more time on it, so I'm not going to do a full rundown. I'm just going to do mostly a rundown. First, let's just start with some results. Uh, so I asked you to fill a grid to below the percolation threshold, at the percolation threshold, and then some beyond the percolation threshold. And these are the results for individual clusters from those three thresholds from a run I did with a box length, a grid length of 100 units. So 100 units cubed. So here I filled this one up to, I think I actually did 25%. I did a little more. This is 30%. And you see two lines here. Yeah, the dashed line is the fit line here, given here, and that's the same thing for here. So 1.88, so around 1.9 is this dashed line. And you can see at low end, less than, say, 100 over here, it matches pretty well. It's very weighted, bottom weighted, right? You get these large guys over here, they start to pill off in that. And I have this black line here, which is something I just put on it that has a 2.5 fractal dimension, a 2.5 exponent, and a 0.6 prefactor. And that's the same black line for all three of these. So let's look at here. So this is below we reach threshold. So this is at 30% full. I asked you to do 20% full. It's not going to change much. So we have mostly everything is here. The largest cluster, I think this was like 2,500. Actually, we can go over here. I sorted so I have all the data here. Oops, sorry about that. So yeah, so our largest cluster is right here, 2,500 monomers. You can see here then at percolation it's 22,000, and then at finally 250,000. So this is filling 30%. That's the 2,500 one. So let's actually go to percolation threshold, which is this guy here, and you still have a big stack of smaller clusters here that follow this 1.9 slope, but you still get this deviation following this 2.5 slope with the 0.6 prefactor. The largest one here, that's at 20,001. So everything's gelling. So that's the percolation threshold. We got that one cluster that's starting to span the system. Then if you really let it go for a while, this is 35% filled. So we went from 30, sorry, I'm using my little laptop today. So we went from 30 here to 31.3116 to 35 here. And 35 here, well, we just have a lot of little ones and then this big, massive guy here that's just sucking up the entire system. And we'll look at those right now. So what I did then is I printed out. So at the end of the algorithm, I have code at the end that does RG, VIN, and in of each individual cluster, and also it prints out the coordinates of the largest cluster in that system. So let's look at that right now. So here's the largest cluster in the first system with 30% full. I think I asked you to do 25. I just took a little longer, let it run a little longer. And there's about 2,500 little cubes, filled spots. It looks pretty open. If you look at the box size is given here. It's 50 by 50 by 50, so it's not even close to filling the spanning the 100 unit space. Then we go to the percolated one, which is this guy here, and you can see the y-axis, which is this axis here, is 100. So it actually started to span the whole space, and it started almost to flatten out here. But it's still a very porous cluster. It's the one that's, if you do you should find this to be, when you do your structure factor, it should be around 2.5. So let's just do, say, about almost 4% more filled in volume. Take the largest cluster there, that's the final system, that one giant guy, and then we got this. The system's completely full. In fact, it's going to crash. There we go. It's just one sponge. It's a cube. So this is probably, if you do the structure factor, it might be, it'll be interesting to see. It's not going to be, probably not be 2.5 anymore. It might be like a 4 slope or a 3 slope. The mass dimensionality, this might be 3. The surface dimensionality might be a little more. It's a rough surface maybe. I don't know. Let's see if you guys can take, this one took a while. At 100, a grid size of 100, this took a couple hours to run. This is all just one cluster I had to pull out of the whole system. But you saw the results here. There were still a lot of individual clusters out there, little small guys, that were still isolated. None of them were above like a couple hundred. So let's go over to the masses here. I have them sorted. So this is cool. The biggest mass is 250,000. The next one's 250, right? The percolation, we have 2 guys that are kind of in the running to be the biggest cluster at the threshold, and then we have a lot of guys around the same mass for the system that's below threshold. So let's go ahead and look at the code a little. So this is a heavily modified version of the code I gave you guys earlier to do. So I cast my grid into a one-dimensional array. So the functions coordinates to index and index to coordinates I already gave you. So these all are the other new functions here. But the only things that actually do in this simulation are these 4 functions here. And I'll go briefly over these. These guys here, these last 4, are just doing the math after I make everything. So it's good to make functions, do everything as many as functions. Let's just check out the main. So I have 4 arrays. I have my grid, my clus lead, clus next, and clus last. And they're all the same size. So that means every spot in the array, even if it's empty, has a lead, next, and last. So it's like you're filling the grid with a bunch of ghost monomers. And only when you turn them on, then they have a chance to make connections. So then I initialize everything. Initialize is just pretty simple. So I zero out the grid. I set everyone's cluster next to -1. I set all the leads to themselves. I set all the lasts to themselves. Pretty simple. Then I have a lot of print statements here. The grid set, let's fill the grid. Okay, this is the while loop to fill the grid. So I know my monomer count I want to go to, which is my monomer goal. I know the number of monomers. Well, it's 0 right now. So I have this random selection. And it only takes in my grid because I'm only filling random spots in the grid. And every time it runs, the monomer number goes up by 1. So this while loop goes until the grid is filled to the concentration I want. Right, so monomer goal is set right there. Just int my percentage times the number of spots. So let's look at random selection. It's pretty simple too. Okay, so what I do is I have an X, Y, Z and an index called place. That's where I'm going to place in the grid. So I just do a random X, Y, and Z. This is this PSD rand. I've used this before. It's just a better random number generator that just makes a random number from 0 to 1. It's included. I've included in codes in the past that I've uploaded. So what it does, it says, hey, give me an X, Y, and Z random from 0 to L, or L minus 1. And then it says, hey, give me a coordinate to index. Give me the index of that. That's the place. And it says if place equals 1, well, then it's already occupied. So then this is why we do this do while loop. So if this is occupied, it's going to do it again until it's not occupied. And then it's going to make that one actually occupied then. And that's the last thing. And then I return place, which is the index we want. But I don't use it. Some people do use it. You could use it and then go ahead and set the grid right then, set to your cluster list. But for this one, for speed, I just set all my monomers and then I'm going to go through the grid and actually make my connections. So then after I do that, I print my grid is filled. Now let's find the clusters. So then I just go to sweep through the entire grid, which is 0 for n. If the grid of that spot equals 1, it's occupied, then I'm going to check and make clusters. So I'm going to check for collisions and make clusters. And that checking is pretty simple. So I give it the particle or the space I want to check. It's a particle because it's occupied, right? I only look in occupied spots. I get the indexes. I have this 3-dimensional array that has an X, Y, and Z coordinate. So that So my X becomes the 0th, Y becomes the 1st, Z becomes the 2nd place in that. And then I have a for loop that's just going to look at my nearest neighbors. So this for loop looks like the nearest neighbors in the X direction. That's what this X2, Y2, and Z2 are. They're the look for the nearest neighbors in X. That's why I'm adding the I here. And then I just convert these indexes to a place. Second place, a potential particle 2. This is interesting here. I have to make sure I never go out of bounds in my array. So I have to make sure X2 is always less than L, and that X2 is also greater than 0. So this is what this is OR here. So either this or this happens, you fall here and do nothing else, then you go over here and you look and see, hey, is that spot occupied? If it's occupied, then we make the cluster, and this is where we join the list. So we'll go over that in a minute. And then I do the same thing for the Y-axis. So this is the same exact for loop. Just for now I'm doing the Y, and now I'm doing the Z. And it returns nothing. So see how handy, another point is how handy it is to have all these done in functions. Because now my main is only like, say what, 50, 40 lines. And I can know what part of each does. Initialization, random selection, make clusters. And I'm calling cluster, you see I'm calling functions inside of functions. So I have this check and make cluster. Well, that check and make cluster actually has the check and make cluster, and also has the make cluster, which is linking the list. We're going to go over that now. So imagine I have two lists, cluster 1 and cluster 2, and I want to make finally a list that's just a new cluster. So what do I have to do? Well, I have to I'm at the glue, so somewhere one of these monomers is touching one of these monomers. So I have to glue these lists together, and what I'm going to do is I'm not going to insert anything. I'm not going to insert any monomers in the middle. I'm just going to say, hey, you come over here. You're the cluster 1, and you're cluster 2. You come over here, and I'm going to just set them on top of each other. So the last is next. So each last has a next of -1. That indicates that, hey, we're at the end. So the first thing I have to do is I'm going to have to set the last of all these guys. All these guys here, their last has to be this last. So we're going to first just erase this. That's the first step. Actually, let's undo it all. Let's make a copy of these because I don't want to straight up erase them all. Paste. Okay. And then we can play with this. So we come here, like this, let's sort of erase this -1 here. So the first step is say, hey, we're going to set the last of all these guys to this. So you set all these guys to that. So we come here, do that. Let's highlight this guy. And boom. All right, that's the first step. And then the second step is that we have to make the next of this guy here, to be this guy. So that's essentially erasing the -1 and making, so we have to make this connection here. Boom. His next is not -1 anymore. His next is going to be the lead. And then we have to make the leader of this guy here, so this guy's leader, is going to be this leader. So we're just going to say, hey, your leader's not this anymore. It's this. Boom. So now we have a continuous list where it's continuous list where we have last 2 and lead 1, and that's the new leader of the new cluster, and these are all the monomers in between, and this is the last of the new cluster. So let's actually look at the code. So all I'm doing is taking one list and gluing it on top of the other list. I'm not inserting anything in the middle. So let's go back to the code, which is done in the make cluster. So I have two particles. Both of them are occupied. I have particle 1 and particle 2. I'm also sending in the arrays clus lead, clus next, and clus last. First thing I need to make sure is if they're not already in the same cluster. So clus lead of particle 1 and clus lead of particle 2, they better not be the same. So if they are not the same, then I do everything. If they're the same, then they're in the same cluster. I don't have to do anything. I can just exit out. The next is I'm going to set the clus last of the new cluster. So clus last, I'm going to set the this last one is a variable that's going to hold the cluster last of the first particle. So this is the last of cluster 1. This is the last of cluster 1. That's why it's called last one. Okay. So then the first step is I'm going to set the clus last of the new cluster, which should be the clus last of cluster 2, which is this here. So how do I have to go through the cluster 1? I have to iterate through cluster 1. This is how I do it. I have this variable nx for like next. I'm going to set that to the top guy of the cluster. So cluster 1's top guy is its leader, which is clus lead of the particle 1. So this is its leader. And then while this is not equal to -1 means I'm still in the cluster. So I say, okay, the last of that guy, which is in this case is the leader, is the leader's last. The leader's last. Yeah, that's kind of hard to say, but it's true. The leader's last becomes the last of cluster 2. And then I say, okay, what's the next of the leader? Well, the next of the leader is cluster next of an x. And so the next guy in the line, his last is the last of cluster 2. And so on and so forth until I go through the entire first cluster and set all the last. So that's the first step. Set the clus last of the join new cluster to the last of cluster 2, which is what we do here. We're setting it to this here. Okay. Step 2. Now we have to join them together. Set the next of clus 1's old last to the clus lead of the clus 2's first, or leader. So that's why I did this first. I set this variable first, because this guy is a particle who's the old last. He's the one who needs a new next. His next right now is -1. Well, it's in the join particle, it's not that case, right? Because we go over here, his next is that right there. So his next should go like that. So we have to actually code that in. This is the code for that. And it's just one line. The next of last 1 is the lead of cluster 2, which is the lead of particle 2. So this is the glue that glues the bottom of the first list to the top of the second list. Then the second cluster, the bottom of the list, needs to get its leader assigned, because its leader isn't assigned yet. So again, it has a current leader, which is assigned here, clus lead of part 2. That guy needs a new leader. His leader is going to be the leader of cluster 1, which is clus lead of particle. And then his next in the line, which is the cluster next of an x, and so on and so forth until we get -1, and then that's it. We have joined 2 clusters. I'm going to post this function, just this function for now, to show you how to join 2 clusters. I'm not going to, I've gone over everything else, but I'll actually have a text of this, and I'll post that. And then the rest is just math. So I have grid math, which is just does math on the grid once I've done everything. It's only taking grid, clus lead, and clus next. And it returns the number of clusters I found. So how do I know if I found a cluster? Well, if that spot is its own leader, and okay, that spot's its own leader and it's occupied. So this means, hey, I'm occupied. I'm not a ghost monomer, right? I've actually been filled with a monomer, and my leader is myself. That means I am the head of a cluster. And then I can go and find my mass. I can find my RG. I could say, hey, what's the max mass? What's the, oops, excuse me for that. What's the max mass? What's the max RG? Print RG and mass, and then print the clust max. So I have a function that prints to a file the coordinates of the maximum masked cluster. Let's look at finding the mass, because that's real simple, and that's how you do everything else in here. So it's again like the clust make. So I just, okay, I'm setting the particle that's the leader, the grid, the clust lead, and clust next. So nx equals the leader of that particle. I could just say, hey, I have to be sure that this is leader. In theory, I could do this for any particle in the cluster. So I say, hey, my leader is this, cluster lead of particle, that's the leader. And then I set my mass here, and my mass just increments by 1 every time. And it says, hey, what's the next? Well, the next is the next of the next. So it keeps going until it hits -1, which means, hey, I'm at the end of the list. And then it just returns the mass, because it's just saying 1, 2, 3, 4, 5. That's all it's doing here. Okay, and that's about it. A lot of people have been asking me questions, emailing me questions about this. I look at your codes. I'm not sure exactly what's going on. They're complicated. It's very hard to read other people's codes. That's why it's, I think, very important to do as many things with functions as possible. So that's one of the big points I want you to take home. Like, this main's pretty clear. It's only a few lines, and I can see what everything happens, what happens at every step. And then all the coding is happening here. So it's like I have, 375 lines by the end of it, right? Print my cluster. But if anything goes wrong, I can narrow it down easier by using this main. Okay, I'll post this hopefully on the 19th. If you guys have any more questions, give me a holler.